So I wanted to start talking about Hooke's law again, and I started last time, but I'm just going to kind of go back where I started from. And we'll talk about Hooke's law today, and the whole idea of Hooke's law is it's a relationship between the stress and the strain. So far we've defined the stress, force per unit area, and we've defined the strain, a deformation per unit original length. And we want to relate the two, and the simplest type of behavior is linear elastic behavior, where the force and the deformation, or the stress and the strain, are just linearly related to each other. And elastic just means that the deformation is recoverable. So if I load it up, something deforms. If I unload it, I just recover all of that deformation, and it just goes back to the original position of the material. Okay? So we're going to do Hooke's law today, and it'll take probably a couple lectures to get through all the stuff on Hooke's law. So let me start again here. Okay, so Hooke measured the elongation of springs under a force. So the elongation I'm going to call delta x, and the force we'll call F. And what he found was for his springs that the force was equal to some constant times the elongation. And this constant here is called the spring constant. So that spring constant is characteristic of the spring, and it encompasses something about the stiffness of the spring material. If you had a steel spring versus a rubber spring, there would be two different stiffnesses for the material. And it also encompasses something about the geometry of the spring, so how tightly wound the spring is, that kind of a thing. Okay? So that's for the springs. But in general, if we have a bar that's linear elastic, we have the same kind of relationship. If I apply a force to it, the displacement or the elongation of the bar is linearly related to that force. And that is Hooke's law for a material. So we can say more generally, if our bar is linear elastic, and isotropic, and if we load it uniaxially, we also have Hooke's law. So let's say I have my bar here. So it has some initial area there, which I'm going to call A naught. And it has some initial length here, which I'm going to call L naught. And then say I apply a force to this, just a uniaxial force to it. So the bar gets a little bit longer. There's my force P. And now I'm going to say the bar is some new length L. And each end here is extended by some amount delta over 2. Okay, so delta is the total deformation of the bar. Then if the material is linear elastic and isotropic, I can say that P over A naught is equal to E times delta over L naught. So the load P and the deformation delta are linearly related to each other again. And the only thing we don't know so far is this thing E. So E is the Young's modulus, and that's related to the stiffness of the material. Okay? And Young's modulus has units of Pascal, same as strength, and that's a measure of the stiffness of the material. And another way that I could write this equation here is just to say that stress is equal to E times strain. And that's Hooke's law for a linear elastic isotropic material. Okay, so we have the stress, like we talked about last week, the strain we talked about last week, and they're related by this Young's modulus here. So that's if I just uniaxially pull on the bar like that. Okay? And materials that obey that are called Hookean. Okay, so Hookean materials. So let me just go over each of these sort of characteristics that we mentioned, the linear, the elastic, the isotropic. So linear just means that the load and the deformation are proportional to each other. Okay? And elastic means that the deformations are recoverable. If you unload the specimen, the length goes back to that original length, L naught. So for example, if I have a stress strain curve like this, if my material's linear elastic, then if I load the material up, so that's loading that way, I just get a straight line. And if I unload it, I just come exactly down the same straight line. So I come back here, and I end up with zero strain, zero deformation back here at the bottom. Okay? So many materials are linear elastic at small strains. And when we say small, we mean strains less than about 0.2%. Something of that order. Okay, so that's linear elastic deformation. Yes?
Do we usually put strain on the x-axis? That just seems like stress is what you're controlling, right? Because stress is from the left force.
This is indeed the way we normally. So the question is, do we normally put strain on the x-axis? And that is what's typically done.
Okay.
Okay. So that's linear elastic. We also said this was for an isotropic material. And isotropic means that the properties of the material are the same regardless of what direction you pull on it. So if I pull it this way or I pull it that way, the properties are the same. So the properties are the same in all directions. So an example of a material that's isotropic is one that has a random structure. If it's random, there's no preferred orientation, and the properties are going to be the same in every direction. So for example, if you took a polycrystalline metal that had randomly oriented grains, then that would be isotropic. So that's isotropic, and we're going to look at Hooke's law in more detail for isotropic materials for a general stress state in a little bit. But we're also going to talk later on about Hooke's law for anisotropic materials. So anisotropic just means that the properties are different in different directions. So if you think of something like wood, wood has a grain to it and the cells are oriented along the grain, and you sort of probably already intuitively know that wood is stiffer and stronger along the grain than across the grain. So wood has different properties in the different directions. It's anisotropic. So linear, elastic, isotropic, anisotropic.